Collisions, direct collisions, type 1, two spheres. In 2010, we have a sphere of mass m and speed u impinges directly on a stationary sphere of mass 3m. Given that the coefficient of restitution between the spheres is e, we have to find in terms of u and e the speed of each of the sphere after the collision. And again, when we're looking for speed here in this question, generally speed refers to the overall velocity. And you'd be looking for normally the magnitude, but because it's only two spheres here, we're only going to have movement in the I direction anyway. In the second part of the question, then it says if E is equal to a quarter, find the percentage loss in kinetic energy due to the collision. Okay, so let's draw a diagram first and then set up our table. So we have m moving towards 3m, and we need to add in that the velocity of m is u meters per second, whereas the 3m is at rest. In other words, it's not moving. So in our table, we're going to do our before, our mass, and our after. So for our first sphere, its velocity beforehand is u, and it's in the I direction. Its mass is m, and then afterwards we don't know what its velocity is going to be once it hits and collides with 3m. So we're going to call that velocity p in the I direction, because there is no velocity in the j direction here. And then we have 0 for the second sphere, so it's at rest, and it has a mass of 3m. So just be careful here with these ones when they're not. Do not assume that they're of equal mass, okay? It's very easy to put in m twice. So its velocity afterwards we don't know, so again we're going to call it q. So for solving these questions when we have two spheres, we always need to look at two of our laws, which is the principle of conservation of momentum and then Newton's experimental law of restitution. And this will allow us to set up two simultaneous equations to solve for p and q. Okay, so we'll start with equation 1, which is going to be our principle of conservation of momentum. In other words, m1 u1 plus m2 u2 is equal to m1 v1 and m2 v2. And you must always sub in for m. Don't cancel m in your head. You must show your m's in your equation, because you could lose marks for that, okay? So we have m times u, 3m times 0 is equal to m times p plus 3m times q. And of course, if we now divide across by m, I'm left with p plus 3q is equal to u. So that's our first equation. So our second equation is going to be set up with Newton's experimental law of restitution. And Newton's experimental law of restitution can be found on the same page as our conservation of momentum, which is page 51 in our maths table. So both of those equations are on the same page under the heading of collisions. So Newton's experimental law of restitution is V1 minus V2 is equal to minus E times U1 minus U2. So of course, if we sub in our velocities after our P minus Q is equal to minus E times the velocities beforehand, which was U minus 0. So in other words, we end up with P minus Q is equal to minus EU, and that's going to be our second equation. So if we line those two equations up, what we have is P plus 3Q is equal to U, P minus Q is equal to minus EU, and of course if I multiply across there by minus 1 in the second equation, that becomes minus P plus Q is equal to EU. We'll call that equation 1 and equation 2, so I multiply the second one there by minus 1. So my p's are gone, And that leaves me with 4Q is equal to U plus EU. And therefore, I can take out U as being common there, which leaves me with U over 4 times 1 plus E. And then if I sub Q into either 1 or 2, I can then get P on its own. So I have P plus 3 times Q is equal to U. So if I multiply out my brackets there, I get 4P plus 3U plus 3UE is equal to 4U. I'm looking for P on its own, so that's 4P is equal to U minus 3UE, and P then, if I take out U as being common, is U over 4 by 1 minus 3E. Okay, so if we go back to the question there, the second part says, if E is a quarter, find the percentage loss of kinetic energy due to the collision. So if we know what E is, that means that I can actually work out these values for Q and P here. So we say part 2. E is equal to a quarter. So therefore that implies then that Q is equal to U over 4 times 1 plus a quarter. So if I simplify that down, well, that's going to give me Q is equal to 5U over 16. And P then will be U over 4 times 1 minus 3 times a quarter. So 1 minus 3/4 is a quarter, and therefore P is going to be equal to U over 16. Okay, so now I have P and I have Q. That's going to allow me to work out my kinetic energy before and my kinetic energy after. So I go on to the next page. So for my kinetic energy, loss will equal the kinetic energy before minus the kinetic energy after. And again, you can work out that all in one go, but just for neatness here in this example, I'm going to do the two separate. So we have kinetic energy beforehand. Well, there are two spheres, so therefore they each have their own kinetic energy, a half m1u1 squared and a half m2u2 squared, which is going to be a half m(u) squared because the second one is at rest. So that would be a half 3m times 0 squared. Okay, so then if we look at kinetic energy after, well, after we have a half m and it's u over 16 squared plus a half 3m 5u over 16 squared. And therefore, if I simplify that, well, that gives me m u squared over 512 plus 75 m u squared over 512. So they have the same common denominator there, so I can just add the top, which gives me 76 m u squared over 512. And that simplifies down then to give me 19 m u squared over 128. Okay. So for the percentage loss in kinetic energy, what we need to do is get the loss over the original. So our loss is going to be before, which was mu squared times a half, minus after, which is 19 mu squared over 128, and that's over before, which is a half mu squared. And to get any percentage, we always multiply by 100 over 1. Okay, so we can see that a half mu squared is common on the top and the bottom. So if I take out a half mu squared, I'm left with 1 minus 19 over 128 on the top. And on the bottom, that's over a half mu squared, which is literally going to divide into that. So then if I multiply that by 100, and I go 1 minus 19 over 128, well, that gives me 109 over 128. Sorry, if we just go back there, half isn't actually common on the top line, that's my fault. So only mu squared is common there. Yeah, so mu squared is common there on the top, and then that should actually be a half inside the bracket. And then the mu squared cancels with the mu squared. So just remove that bit there. Oh. Blue. So the mu squareds cancel. Yeah, that's better. Okay, so the mu squareds cancel, which leaves me with then a half minus 19 over 128 over a half times 100. And then that gives me, as a percentage loss, 70.3. So in other words, my percentage loss in kinetic energy is 70.3%. All right, so in terms of mark breakdown then, we had 25 marks going for the total question. So I just put that at the start, that's 25 marks. And we had 5 for setting up each of our equations. So 5 for the first, 5 for the second, and then 5 for getting our P and our Q, so the two together. We then had to get our kinetic energy loss. So our loss at the end was 5 marks, and then for getting the kinetic energy before and after, we were getting 5 marks. So that was 5, 10 for the second part, and then 15 for the first part. Okay.